we will finish our seminar, and at the same time, I'm going to introduce our next speaker.
Okay.
Then that's it. And after the seminar, our university considers that your presentation would be very beneficial, not only for our department, but also to other people who would like to share your presentation. So they are going to have your presentation material on DGIST YouTube. Do you think it is okay for you?
It's no problem. I think it's okay. It's no problem.
Okay. Thank you very much.
Yeah, after I finished the talk, then I just how to say send the PPT and also was in PDF file to you.
Yes, wonderful. Yes. And so the DGIST is going to your presentation to announce that we are having such a wonderful seminar series. That's the main reason, you know. I'm very glad you understand that. And let me see whether I can have a screen share. Okay. So it is something like this. Can you see?
Yes, perfectly, no problem. Perfect.
Yeah.
So maybe
yes, it is like this. And I will show your very handsome photo and your affiliation with the title. Then this is your brief CV. Then after this, I will switch back to you so that you can use screen share function.
Okay.
Okay.
So when I talk, I will stop my video. Maybe some the internet is
yes.
Not.
Oh, yeah. Wonderful. And perhaps you can recognize some of our colleagues which are working on battery. And one of them I can see at the moment is Professor Youngmin Lee.
Yeah,
and maybe you have met him already.
Yeah,
I think.
the face is very familiar with it. Yeah, I think we meet
yes.
some in conferences and somewhere.
Yes.
Yeah.
And right. I'm sure there are more colleagues. And let me see who else. Professor Ho Chun Lee perhaps is here, and
I'm checking also, but no other professors now. They are coming, maybe.
Yes. You are such a famous professor, so that they want to miss your seminar.
No, because sometimes I handle some paper in the journal sources, so I know many Korean professors. But sometimes it's very difficult for me to remember his name. Sometimes.
Yes.
Yeah. When I meet where I know, oh, who is who. But sometimes where I cannot remember the name, so I must do by this way.
Is it possible for you to increase your volume
Okay.
Microphone volume. Yes, a little bit more.
More? It's
Yeah,
okay?
it is perfect. Yes,
Oh,
yes.
okay.
Okay, wonderful, wonderful. Well, it's 27, so we have a couple of minutes more. So what else is new in Fudan University?
Pardon?
What else is new? What's the new thing happening in your university?
New thing?
Yes, your university, Fudan University.
Yeah.
Something
Nothing
new.
much. And we know everything about Shanghai now.
Yeah, you may be from news. So.
Yes, news. There's nobody on the street. Nothing.
Nobody, no car.
사진 찍었어.
Yeah, that's right.
왜요?
Yeah.
우리가?
작년에는 끝날 때 인증사진 찍어야 출석 체크도.
I hope you already stocked
진짜로?
many foodstuff so that you can live
근데
without.
저번 시간에 조교가 찍는 줄 알았는데.
아니 저 찍었어 저번에.
지은 학생 지금 소리 켜져
안
있어요.
찍었는데. 조교가 찍는 거 아니에요?
그게 찍는데 저 화면 난 안 켜놨어. 안 켜놔도 되나 싶어.
So Professor Xia, it's time to determine whether we are going to join ESES meeting held in Vancouver. Is it possible to join that conference from China?
No, recently it's how to say not only Shanghai, so it's very difficult to join the. We do some online conference. Yeah.
So in Korea, some professors, students are thinking to attend the conference now, because if we got vaccinated 3 times, it's no problem to go to work or go to school, no problem. So it's possible officially, but it's not easy to determine.
Yeah. Most university in China now is students must to stay to the dormitory. So we also stopped to working most. It's impossible to do some experiments.
Okay, I see.
They also can do some to write some review. I asked the student to write some paper on with review paper.
Well, I think now it's time to start our seminar. And welcome students and professors to our regular Thursday afternoon seminar. And from today, our department is trying to new attempts to invite very distinguished foreign professors to deliver us a seminar, partly due to the COVID problem. And today is the first day of such 6 distinguished seminar series. And I'm very proud to introduce Professor Yongyao Xia of Fudan University, Department of Chemistry and Shanghai Key Laboratory of Molecular Catalysis and Innovative Materials. The title of his talk is Intercalation Reaction in Aqueous Electrolyte and its application. And before he starts his seminar, I would like to introduce him briefly. And he got his BS degree from Department of Chemistry of Zhejiang Normal University, China, and master's degree from Jilin University, same department, in 1990. Then finally got his PhD degree from Materials Science of Saga University in Japan. Then after his PhD, he spent a year as a postdoc fellow at the University of South Carolina, Department of Chemical Engineering. Then another couple of years at battery section of Osaka National Research Institute of Japan. Then after that, he spent a couple of years as a researcher at Hitachi Maxwell Company in Japan before he took his current professorship at Fudan University. And he got various awards, and among them, I will introduce only several today. And first, he got Outstanding Young Scientist Award from National Science Foundation of China in 2009, and Contribution Award from Chinese Society of Electrochemistry in 2015. And then first prize of Natural Science Award of Ministry of Education in 2016, and Technology Award, Battery Division of ECS in 2018, and IBA in 2019. Then he was elected as a highly cited researcher from 2017 to 2021. And then he became ISC Fellow in 2019. And he has published almost 400 papers, 3 book chapters, and 30 patents. And his research interests are lithium-ion batteries, electrochemical supercapacitors, and new battery systems. And please welcome Professor Xia for his presentation. And let me close my screen share so that he can screen share for us. Please, Yung Yao.
Okay, so I try to share, but wait, what problem? But it's probably I was controlled by your side, so it's not promised to my to switch the. Oh, it's no, maybe it's okay. No, it's impossible.
We don't see yours yet.
Yeah, maybe you must how to say, close your.
Oh, I thought I closed this,
Yeah,
but
you must.
still I can see it here.
그 교수님 공유 권한 넘기셨나요? 그
위에 있는 걸 눌렀는데 아래 보니까 아직도 있어. 그래서
네, 화면 공유해서
비활성했습니다. Okay, now they
yeah.
now you can use screen share.
Yeah. Can you see my?
Yes, yes, wonderful, great.
So I start my talk.
Yes, please.
So at first thing, I would like to thank Professor Kim, Dr. Lee, to give this chance for me to give a talk on this energy seminars. similar. So today I would like to talk some intercalation reaction in aqueous electrolytes rather than in the no-aqueous electrolytes, and also talk some in its application, new application of this one. Right? So what problem? Right? Sorry. So my computer system. Right. Sorry, just wait a moment. So it's because I cannot show the whole window. I don't know what's the problem. So just to show this is I can move it, so no problem. Sorry. So no. So before going to my talk, no, it's okay. The screen. Hello.
I guess it's okay. You can get started.
Okay. So before going to my talk, I just very briefly to introduce our university. So
Yes.
Fudan University, Fudan University is located on the east of China. So it's a Chinese map like the chicken. So we just looking in here. So I think it's very near to the Korea. We just take it to about 1 hour by airplane from Shanghai to Seoul. And Fudan University was established to 1905. It's about over 100 years. And she is a top 3 university in China. Sometimes it's rank 5, 3 to 5. So Shanghai is very beautiful cities, but no, it's have a very serious conditions. So it's very, if you have been to China, you will maybe to Shanghai, we have the Huangpu River. This is the Oriental Pure. This is a signature sign C. And this also is Fudan University. We have the 4 campus in Shanghai. So we located, our department is in a new campus. So my group in China is not so big. We about 30 people. We have 3 staffs and about 25 students. We also have 1 Korean students from Jiaquan University. So he started his he can speak Chinese frequently. So our research group is not so good, not so big. It's only about 30 people. So as Professor Kim already just thank his detailed introduce. So my main research is focused on the advanced material and the technology for energy conversion and storage devices. We're doing some lithium sodium ion batteries, like aqueous or no aqueous electrolytes. We're also doing electrochemical supercapacitance, and also do some new battery systems. So for the most commercialized materials, we doing some we study the charges in the crystal structures like lithium spinel, because I do many work in the Japan for the spinel structure lithium manganese oxides. We're doing as the high cycling stability lithium titanium oxides. We are also doing some lithium ion manganese phosphate, and also doing high capacity lithium rich the NMC, and also very recently we've been doing the sodium iron phosphate. And we also study some, because in the aqueous electrolytes, later I will go to the details because there is some problem. So we study some competitive and selection reactions for the ion in the aqueous systems. So we developed some aqueous lithium ion battery, and we're also doing some seawater desalinations and material splittings, and also doing some splitting the electrolytes use the battery materials. And recently, we're also doing some battery mechanical trains. And also, we study some solvent chemistry and interface reactions like low temperature batteries, and also some solid state batteries. Besides this, so in the early of my research in China, I doing some study some ion transport and storage in the pulse. So I very often to attend the supercapacitance conference, and we doing the mesoporous carbon materials and also some lithium hybrid capacitance. So now just go to my talk. So everybody in the field of battery, we know in the 2009, so 3 scientists was awarded the Nobel Prize was they developed the lithium ion batteries. So lithium battery have very widely used for commercialized for the many applications. For the high energy, the small batteries we used for the 3C markets, including the computer, camera, and the consumer electrons. And for the small power batteries, we use it for the power tools, and for the large power battery, we use the electric vehicles as well as the e-bus. And for the large scale battery, it has been or will be to use for the energy storage materials. So what's the different tendencies of a battery in the both of the industry and the academic? So I think this is hard to develop the high energy density battery is still a hot topic in both in the industry and in academic. This include develop the high capacity cathode and anode, high voltage cathode material, and also wide window electrolytes. And another approach to improve the energy density is going to the lithium metal anode material batteries like lithium sulfur and lithium oxygens. But from the high safety videos, we developed for the industry, we still developed the high safety lithium ion batteries. But for in the academic research, we're going to there is another approach, directions is from organic liquid electrolytes to the aqueous electrolytes and the solid state electrolytes. And also from the low cost is from the lithium ion to sodium and melted ions, but including magnesium, calcium, and aluminum, and with some low cobalt cathode material, and also as well as the organic electrolytes. And from the environmental tolerance, recently we are with much research as moved to the high temperature or high pressure or low temperature or the high powered batteries. So let's go into talk the intercalation. Everybody know in 1976, so Professor Whittingham for the first time to propose the intercalation for reactions for the batteries, And then in 1980, Professor good enough to develop the cathode material lithium cobalt. And in 1985, in Asahi company, Professor Dr. Yoshino to apply the polyacetylene as a negative electrolyte and combine the lithium cobalt. And 3 science, they was awarded the Nobel Prize of chemistry in 2091. But for the, and then Sony company commercialized the lithium-ion battery in 1991. This is based on the organic electrolytes. Is a no accurate electrolytes. And for the accurate interconnection in the accurate electrolytes was the first thing is proposed by Professor Jeff Dunn, is a very famous scientist in the field of batteries. And in 1994, he developed a vanadium as a negative electrode and spinel as a positive electrode. And unfortunately, this battery only can cycle in 10 cycles. And then because this is a two power cycling stability, and very few science research focus on these directions. And in 2005, so our group applied activity carbon as a negative electrode, and we greatly improved the cycling stability of the Aqueous systems. And then in 2010, because the active carbon lithium spinel system is a low capacity densities. So we in 2010 we introduced lithium titanium phosphate as a negative combined with active carbon as a negative electrolytes, as a negative electrode. And then this is the lithium-ion battery, accurate lithium-ion battery was commercialized in 2000 in Aqueous Energy. This is an American company in 2012. And in China, we licensed this patent to N-Power Energy to 2015. So let's see the difference for the ion interconnection in no-aqueous and aqueous electrolytes. In the no-aqueous electrolytes, so normally is dissolved ion interconnections, but for in the aqueous electrolytes, sometimes is dissolved and also sometimes is solved, depend on the cathode materials. And for the no-aqueous, normally is single metal like lithium, sodium ion, but for the aqueous systems, there is a proton and metal ion competitive reactions. And for the no-aqueous, it's normally where the electrolytes will decomposite, and the decomposed product is mostly indissolved in the electrolyte solvents. So most we have formed some SEI layers. But if in the aqueous systems, most solvent is water. So normally is because, and another is that if the electrolytes decomposite, normally is dissolved in the water. So normally is without SEI layers. And in the no-aqueous systems, normally have a stable and wide electrochemical potential window. But for the aqueous systems, normally have a narrow electron windows. It's easily to have hydrogen and oxygen evolutions. So today I will talk the four directions. The first thing, we started some competitivity reactions for the protein and metal. We developed the aqueous lithium-ion batteries. And then I will try to talk some research on some seawater desalination and material splitting using by the interconnection in the aqueous electrolytes. And also we use some battery materials as a charge medium to splitting electrolytes, as just is decouple water to the hydrogen and oxygens. And very recently we use a battery to do some battery medical trains like antitumor therapy. So first thing, talk about the lithium-ion battery, accurate lithium-ion battery. So lithium-ion battery, theoretically, and lithium-ion battery, accurate lithium-ion battery can be assembled by combined low potential anode materials the potential like 2.5 volts and a little high potential the cathode material, the potential about 40 volts versus lithium. And within the oxygen hydrogen potential ranges. So this was a voltage will be at 1.5 volts. And then we can count the specific energy will not exist 50 watt hours per gram. This is based on the practical batteries. So the specific energy density is closer to the lead acid batteries. So this just shows the electro materials for aqueous lithium-ion batteries. We have a lot of choices. This is called the oxides and polyethylene materials and other some materials like the organic electrolytes. So, but most commonly from the cost, from the potential and some potential and the stability of these materials. So we choose some commercialized lithium-ion cathode material, and also we use some lithium phosphate and activated carbon as negativity. And most vanadium-based materials, because it is dissolved in the water, is not check chemical stability in the waters. And these materials normally is low potentials. So from the industrial applications, we choose this currently commercialized cathode materials. And we also use activated carbons this way. This can hold the adjust the electrochemical window of the aqueous lithium-ion batteries. So, but the most interesting, we applied a microelectrode. We use the 50 micro platinum microelectrode to do cycling water gram of the spinel and layer structured materials. It's quite interesting. For the spinel is stable in span of the pH volumes, and it's stable in the pH from 7 to 13 to 30. But for the layer structured materials is not stable in the low pH volume, the electrolytes like pH volume 7, but is stable in the high pH volume. It's the alkali electrolytes, like for the example for the pH 11 out of that. So what is happening to this one? At first thing we applied the first plain simple to calculate the lithium-ion division passes and bases of lithium cobalt. This is when it's structure the layer spinels, the layer structure NMC is the structure is similar to the lithium cobalt. So because in the aqueous systems, there is protein. So if protein is present the position of the lithiums, for example, for present 1, the total is 6 wave plus 1 and 2. So the division value will become high. So this suggests if the lithium present the position of the lithium protein presenting of the lithium positions, because oxygen and lithium and hydrogen is very strong bind. So this protein cannot de-interconnect and cannot be de-interconnected. So we use the AC impedance to check this at the different oxygen states. So it's very most interesting one is when you are discharge process. Charge process like this is B, and then we discharge. But after discharge, so this protein, so our this position we observed another semicircles, and then we think this is the first thing in the charge process, just the lithium de-intercollections. But for the discharge process, there's lithium and protein, both is the intercollection. But this is dependent on the concentration of the lithium and the hydrogen. So we did some theoretical calculations, and in the high pH volume and the low lithium contents. So this in the high pH volume and high lithium contents. This is stable for lithium intercalations. But for the low pH volume and low lithium contents, this is mostly unstable, this one. So we chose the spinel because the layer compounds electro materials like the layer structure NMC on the lithium cobalt. It's impossible to apply the inaccurate electrolytes. So we choose the spinels. Spinels we can develop the different morphologies, lithium spinels. So we can also very recently we can develop the spherical spinels. And for the cycling stability, and we can control the lithium contents to adjust the cycling stability and the capacitors. For the lithium-rich compounds, we can normally have the very good cycling stability, and for the just LMNO4, we can get as high as capacity 130 milliampere hours. So this depends on what you want. If you would go to cycling stability, we use a lithium-rich one, and for the high capacity, we use this one. But the cycling stability also depend on the surface area. Very recently, we use this type of one. We can get a good cycling stability of aqueous systems. So at first thing in 2000, I think this is 2005, we just Professor down to use the vanadium oxides, but the vanadium oxides is easily dissolved to the water electrolytes, and we use activated carbon, and this is we call the accurate lithium ion hybrid supercapacitors, like rocking chair batteries. So for the conventional supercapacitors, normally is the electrolyte will be consumed in the charge process. But for this hybrid lithium high supercapacitors, in the whole charge process is lithium. This is involved lithium insertion and extraction reaction in the cathode material, and then in the anode in the active carbons is ion adsorption or deabsorption. So is the concentration, the electrolyte concentration is constant, is not electrolyte consumed. So this commodity is quite different from the conventional EDLC electro double layer capacitance. So we get a good cycling stability over the 20,000 cycles. This is laboratory cells, and we can get the specific energy of 35 watt-hours per gram. And if we use a practical cell, it's about 10 kilowatt-hours. And then we cooperated with one Chinese company in Shanghai, and this is a very famous company for the supercapacitors. So this is very early work. We did some hybrid supercapacitors, and this capacitor really can good cycling over the 20,000 cycles with the capacity limitation over the 70%. And we use this better high supercapacitors. We applied in the 2000 Beijing Olympic Villages in the solid white in the hill. I think this is here in the end of the ground, this one. And but this hybrid supercapacitance is because this specific energy density is low, is about 10 watt-hours. And then we introduced the lithium titanium phosphate, But this materials shows I think it shows that it can synthesize at a high temperature over the 90 degrees centigrade. So normally have the small surface area. And another is this is a nice strong materials is have a good cycling stability. So we can get the good cycling stability, this one. But the problem is this one, we use these materials, and we use the carbon coated materials, but the cycling stability over than 200 cycles, but still have the 10% capacity losses. So what happened to this one? So problem is this is so in 2010 we published one paper in the Nature Chemistries. We found that for most another materials like lithium iron phosphate, if present the oxygen and water, so this oxygen and water will oxidize this lithium titanium phosphate. And for the cathode material, it's no problem. This is a bigger problem. Even we use the carbon materials, but if we present the oxygen, this will be oxidized. And for most researchers, they will doing the accurate lithium batteries will in the open the systems. So this problem is normally with very often often take place. This one. So this is very important point for the accurate lithium systems. And this is just this means that for accurate lithium-ion batteries, we must seal this way. But if we call why is there some, if we go back to think over, for most of the accurate system, the batteries like lead acid battery and metal hydrogen battery, it's normally is sealed one. Why is supposed? But because in the accurate electrolytes, the oxygen and the hydrogen and the oxygen will be evolution. This we cannot, how to say, avoided. If the overcharge the water must be decomposition. So why is this batteries can sealed? Because we have, even for the metal hydrogen in the discharge process is a protein is how to say intercalated metals, and this will be self will oxygen by the will be oxidized by oxygen. We call the oxygen self-elimination reactions. Even for the lead acid battery, because this is the lead, also is a lead, but also can be oxidized the oxygen. We also have the self-elimination reactions. So this suggests for the accurate lithium battery, we must find some oxygen self-eliminated electrode. Then we can hold the seal the accurate lithium-ion battery. So we take the many over in 2 years to find this one. We find some polyimidal electrolytes can have the oxygen self-elimination functions. For this is also is active materials in the discharge process. This is a bond, carbon bond will open. And then we will combine the lithium. So this can store the energy, can storage the lithium. But this material can be when chemical oxidize oxygen and go back this one. So this is self-elimination electron materials. And then we coupled with one company. We use this is a construct of the accurate lithium batteries. We use the anode material and the solid material as a splitter and manganese spinel as a cathode material. But we must, because for accurate lithium is open voltage is very low, around 1.5 volts. Normally we must propagate the thick electrodes. So, and then we in 2005 we have patent we use just I moved before. This use a spinel as a negative positive electrolyte, and it contains the activity carbon and lithium titanate, lithium titanium phosphate. And then with this license was this patent was licensed to air power companies 2000. And then we commercialized the accurate lithium-ion batteries. So this battery we can get the energy density at 26 watt-hours per gram, and it can over 30 cycles. And this one. And then this is I think this Aqueous systems is very it's very observed safeties. You even saw we doing this way. So this is very good. And also we is by this is also is working well. Anyway, this is very supportive. So this is just summarized how to progress in the aqueous lithium in our group. We developed this one in 2005, and then we commercialized it in 2014. And then we developed a much more good cycling stability aqueous lithium by using titanium phosphate, because this potential is a little higher than the lithium titanium phosphate. So it's this way it can observe to avoid the hydrogen evolutions. And very recently we moved to the aqueous sodium-ion battery, because sodium-ion battery will be much cheaper than the aqueous lithium-ion batteries. So we hold a national key research development program of China from 2006 to 2021, and this is the program is special service for the smart grid technology and equipment for the for the smart grid technology and equipment, and we cast the basic research on the sodium-based batteries with high safety and long cycling life and low cost. So we developed, this is Chinese. So we developed two systems. One is aqueous sodium-ion battery. Another is solid-state lithium sodium batteries. We use low-cost materials, and then also for the we take for the aqueous and sodium-ion battery, we still have the many electrical materials, but unfortunately, most sodium cathode material is dissolved in the water. Really, we can only see sodium 0.4. This is a tunnel structured material. This is stable in the aqueous electrolytes, but most materials like sodium vanadium phosphate is dissolved in also some organic electrodes also dissolved in the water. So we choose that, but for the anode negative materials, we can use the sodium titanium phosphate, and we propose the lithium because we cannot find some suitable sodium-based positive electron materials, and we use the spinos. This is hybrid sodium-ion batteries. It's normally we can get the specific energy density about 30 watt-hours, can over that 1,000 cycles with a capacity limitation of over 78%. And this way takes 5 years to develop this one. So, sorry. So for the key, for the aqueous systems, we already commercialized the one, but the cycling stability and the specific energy still is limited. So for example, still have the drawback of the aqueous systems for the low energy density. I think about cannot over 45 or 50 watt-hours, and on cycling stability is over at least we should over 5 cycles, and also have some collected the Cluyon problem, and the electrolyte we still have much work can do for the electro and banded designs. For the specific energy, we must find some because the potential window is still low, and another problem is the overpotential of we must increase the overpotential of hydrogen oxygen evolutions, because in the practical batteries, that the water decomposition must be avoided. Otherwise, the electrolyte will consume it. This is one. This is the main, how to say, filter mechanisms of aqueous electrolytes. So we must observe to avoid the water decomposition in the practical series, because the electrolytes, the content is limited in the practical batteries. And the other one is a cycling stability one. We must do some like manual work, and another is plotting the competition, the election likes, and this is one. So let's go to the we use some for the electrolyte, the splitting electrolysis. So really for normally we call some energy crisis one, and really we can use if we can use a substandard energy. So we have a bounded green electrolyte from substandard energy, and this have two ways. Another is we use a solar cell, and we combine with the stationary power battery storage, stationary power sources like lithium-ion battery can stable storage in the batteries for this one. Another we use some solar and wind turbines energy directly utilized, for example, for the electrolysis, and this one. And more up to date, main research of water electrolysis is to develop advanced catalyst to reduce electron overpotentials and to save the electricity. So there are many papers like published in Nature Science and some Nature Materials and so on. And this if this just is in with the purpose is the aim is in reduce the electron overpotentials. And then from another, if we check the states of industrial hydro productions, so there is 3 ways to produce hydrogen. One is use fossil products. So this is cheap, really is cheap for about millicubic for about $0.3. And this is most is the market is over than 90%. And for this if we produce the fossil products, is high impurity and need to be purified. So we cost, so it really will very cost. Another is used for the with electrolysis water, just use the common electricities. So it's a very high costs. But we use the substandard energies. This is just directly used. So it's we can, so the cost is same as the fossil products. So the most promising alternative approaches to list the cost is used the substandard energy, directly use the substandard energies. So we think if we can use the fossil, use the substandard energy, so we can reduce the cost of the hydrogen. So the cost of hydrogen now is going to say this is a big drawback for the hydrogen using this one. And then our challenge, our approach is to if we see the commercial combination the electrolysis, no most is we use the alkaline water electrolysis. This is mostly use the hydrogen productions, because this for alkaline electrolysis is cheaper than the acid PEM acid electrolysis, like use the PEM, use the ion exchange membranes. So, but the problem is there is a risk of mixing during the simulating the product hydrogen oxygen. So oxygen and hydrogen will steadily evolve this way. And then to the pollution on both on the anode and the cathode side, the cell must be equalized at all times to prevent the gas crossover through the porous cell batteries. So suggests we must need the stable voltage input. So it's very difficult to utilize the substrate energies. So this is the conventional the alkali electrolytes. So then we use the nickel hydroxide. This is a pollutant intercalation for the nickel hydroxide. So we separate the oxygen and hydrogen oxygen evolution. So for the first thing, because this for the oxygen potential is between the hydrogen and oxygen evolutions. So this reactions is the potential is higher than the hydrogen evolutions, but it is lower than the oxygen evolutions. So we can separate this water electrolysis by two steps. The first step, this is just the oxygen. But it's in the anode. This is short is cathode. This water was reduced to hydrogen, but in the cathode, this is nickel hydroxide to Ni to oxidize the nickel OH, and then in the next step, this is just charge. This is a discharge process. And then in the discharge process, this oxygen, hydrogen, OH will oxidized by oxygens, but this is NiOH will reduce the nickel hydroxide. So we can split the oxygen and hydrogen, oxygen and hydrogen to separately to evolutions. We have many Chinese patents. We also have many papers in this. And then when you see this in the first steps, and you just see very quickly to see the videos. So this is a hydrogen evolution electrodes, and you will see this is oxygen hydrogen evolution, but you cannot see the oxygen hydrogen oxygen evolution on this electrode material, or this materials, and this one, and you will see here. And then, so by this lectures, we for the first steps, we can use the oxygen to produce the oxygens and this nickel hydroxide, this one, nickel, and if this nickel hydroxide will oxidize the NiOH, and if we combine with the zinc and the negative electrode, this is assembled as a nickel NiOH and zinc batteries, so we can discharge the way. So that in the daytime we can use the solar or wind to produce hydrogen in the daytime, but in the night time we can use the zinc nickel batteries to produce power for the electricity. So it's very interesting that this one we can use for the battery material for the reaction in the aqueous electrolytes as a charge mediums to separate the oxygen and the water. So, and then we can use if we use the sodium battery materials for the NN044, this one is stable in the aqueous electrolytes. We can separate the core alkali electrolytes. And in the first steps, we just this is a discharge. This is sodium will extract from 0.444 this one, and then oxygen water will be oxidized the oxygens. We will reduce to the hydrogens, and then for the discharge process, this one and this one will discharge to become for 0. Go back this one, and this is the chlorine ion, and will be oxidized the chlorine this one. So we can separate this core alkali electrolysis, and then we can also use because this sodium sodium titanium phosphate. This is a gold materials for the lithium, for the sodium and sodium intercalation and de-intercalations. We can use this one for the seawater desalinations. We combine with activated carbon in the discharge process, in this discharge process, the sodium will be intercalated lithium titanium phosphate, and chlorine will adsorption on the activated electrodes, and this is the seawater will become a distillation the waters, and this will consume the energy about it. For this one about 2,000 millijoules, and then we can use this one. This shows the size electrical performance of this. Like is hybrid supercapacitance. It's used as a good cycling, good power because, and also is good cycling stability. And then we just use this cells. If the primary electrical consumption of the sodium chloride is of 0.6 mole, and after we'll charge it to 1.6. So this is the electrolyte, the concentration will reduce to 0.3 more. So this is desalination, this one. And this is also we use with not concentrated sodium chloride solutions. So this is as dependent the battery voltages. So if the high voltage, so will reduce the concentration is greatly. And we even depend on the voltage and also depend on the capacities for this one. And finally, I will just very simple to talk some self-deoxygen behavior of organics with carbon oxygen double bonds. As I mentioned just before, for this polyaniline is kind of self-charge, oxygen deoxygen the behavior of this one. So this materials, so this polyaniline immediately can stop when in the discharge process, so can stop the lithiums. But if we present oxygens, this is discharge cover of this one, and then we put there. We just is chemical charge, not electrochemical charge. We just present oxygens. So this discharge cover will we go recover to the charge covers, and this is dependent on the time. If we over 10 hours, so this battery can completely by the chemical oxidation, chemical charges, and you will see this is just 1 hour, and 1 hour after discharge, then we just stay in the oxygen atmosphere for 1 hour, and then for 10 hours. So over 10 hours, so this completely is how to say, the capacity is same as electrochemical charges one. And then we see the oxygen. We use the fluorophenoxylene as an index to check the pH volume changes. For if we with the oxygen, because this will discharge, and then oxygen will discharge in the discharge process will produce OH. And then this material will oxidized by oxygen, and this OH, how to say, the concentration became bigger and bigger. So it is the color, the pink color became much more pink, this one. But if we without oxygen, you will see in the first thing, because of discharge process, the OH, so this became pink. But in the charge process, is go back this one. If we the polyene, so this pink, it will disappear, this one. And then you will see, because this is how to say, for the anti-tumor therapy. So normally we use high we call it is hypoxia materials with tumors is necessary and important conditions. So we must use high porosity the atmospheres for the high porosity activity projects. So this projects, if we have some effect, so must is high porosity. So then we use this oxygen self elimination reactions. So this is high power sequencing the active products can work well. So we use the, if we combined with this, we also call the TPJ. This is one kind of atypical drug of HPS. There's a high potency active products. And you will see, this is just the common one. This is this is thermal. This is thermal in the thermal. But we use the self-discharged batteries. This is also the thermal will disappear. But if we combine it with the TPJ, this is one kind of LPS. So this is the thermal. Thermal is disappeared completely. So because this how to say, drugs must work without oxygen, so it can work. So we use this battery. We can how to say, apply it for the antitumor slappings. This one. So finally, time maybe very close to close. So conclusions is accurate lithium-ion battery use intercalations in the multi-electrolytes, provide most potential for electrical energy storage applications, but it still have low energy density and limited cycling life during the electrical window and current collected corrosions. This one. So we use the nickel hydrogen as a recycle with the redox material. We also with charge materials, we can decouple so we can successfully split the conventional alkali electrolytes into two steps. So we can use the flexibly use the suspended energy like solar and wind power with high efficiency. And so for the intercalation or some electrochemical reaction in the aqueous electrolytes, we can use in the seawater desalination and material separations and also antitumor slappings. So thank you for your attentions.
Well, thank you, Professor Xia, for your very nice presentation. I appreciate very much. And it's time for questions or comments. And first, I would like to ask students for questions. Students can leave question in the chatting panel as well. Oh, there is one question.
Okay.
I wonder what you think. Can you read?
Yeah.
So one
Please.
student ask you the future about the Aqueous zinc batteries.
Aqueous zinc batteries, yeah. I think aqueous zinc batteries is also very promising systems for the aqueous electro batteries. So I think we recently we're also working on the zinc-based aqueous batteries. I think this is the specific energy is much higher than our systems. We use the intercalation reactions because we use the zinc negative electro materials. So we think these batteries have an energy density over than 60 watt-hours per gram. It's possible to get the practical batteries can get the 60 watt-hours per gram is much higher than our intercalated systems, about 30 watt-hours per gram. But it still have some bigger problems from the experiences of our accurate batteries. We think the mild electrolyte, like neutral electrolyte, this is the bigger problem for the accurate systems, including the zinc-based batteries, because it's if the pH volume near the 7, so it's very difficult to control the pH, the oxygen and hydrogen evolution. This is a big problem. This is one. And the second one for the zinc batteries, I think the zinc, even we have the some approach to provide to supplies to suppress the zinc dentalize, but the zinc will chemical or and the electrochemical reaction with the water. This will we cannot observably avoid the hydrogen evolutions. This is a big one. This is a bigger problem. And another one is the cathode materials. For the zinc battery, still we have some cathode material like the vanadium one and the manganese one. But this is not the reaction. Mostly is the materials for the vanadium. It's impossible to use for the aqueous systems because vanadium is have high dissolution in water. I think it's really if we have the limited cycling stability for the zinc ion battery, for example, 1,000 cycles. So the zinc batteries, it's have a possible for commercial life. But for the longer cycling life, I think it's very difficult because it depends on the systems and the electron materials. But still I think we have many work to do, like I just mentioned, like to know.
Any other questions? If not, then professors.
And thank you for your wonderful talk about the Aqueous battery system. So it is very helpful for me to follow up state-of-the-art technology and progress in industry. So, and then I am surprised that you fabricate the prototype, the Aqueous battery system, is it right? You are engaged in making those kinds of prototype, the Aqueous battery?
Yeah, protein. Yeah, we did this one. We are group. We are also doing this one. But mostly for protein, we use the most for the organic organic. For the electron material, we use the organic electron materials normally.
So from the slide, I quote the number for prototype 1, 26 or 25 watt-hour kilogram. Is it right? For Aqueous, the lithium-ion battery system. Page number 9, maybe. Okay. 25. Yeah. That's right.
Yeah.
25. 25. The number of 25 is similar to that of lead acid battery. So I know. Comparing to lead acid, they are using the sulfuric acid. So your system may be better as a point of environmental impact, but the number is not high. So there are any room to increase the energy density of your system or any other advantage comparing to conventional lead acid battery system?
So at the first thing I showed introduce the advantage and disadvantage of these systems. Compare the lead acid batteries. The conventional lead acid battery normally have the cycling limited maybe 5 cycles for 500 cycles. For example, for the electro bicycle, so about 300 or 500 cycles. So for those batteries, the specific energy about around 35 or 40 watt-hours per gram. So it's limited, but the cycling stability is low. This one. So I think for this aqueous lithium batteries, the possible potential application markets will be energy storage batteries for the stationary power sources, not instead of used for the electro bicycles because the specific energy is low. But for the lead acid battery, there is a new approach use the carbon. We call the carbon. We introduce some activated carbon in the negative electro material, and this is we call the hybrid lead acid battery. So for those batteries, the cycling life can extend to 3,000 or 5,000 cycles. but the limits are, unfortunately, the problem is for this type of activated carbon acid batteries. So we can only charge discharge with 30% DOD. So the capacity really, the used capacity specific energy is about 10 watt-hours per gram.
Okay.
So this is much, because we cannot full charge discharge with 100% DOD, because the hydrogen will evolutions if we use 100 DOD charge discharge. So we're limited about 30% DOD. So compare this one, so we have some advantage of the accurate system. And from the risk for the we can use, because for the solids, for the stationary power sources, so mostly use the lithium ion battery or use the lead acid. But for lithium ion battery, sometimes we have the, how to say, the walls have the risk of the safety problem of accurate for the lithium ion battery. And also because we use sulfur acid, so with environmental problems. So for there is some special markets we think have the accurate lithium ion battery have the potential. But the problem is the space. There is two problems. One is the specific energy is low, and then this is the cost. That really the cost for accurate lithium ion battery is not so cheap because the specific energy density is low. So I think we really because most material is dissolved in the water, so we have not much choice to select some materials, and we can do for the negative materials, maybe we can use some zinc and what is combined with some intercalation compounds. But for positive one, it's difficult.
Okay,
So,
I see. Much longer cycle life under the 100% DOD is the merit point for your Aqueous system, but the cost still high comparing to other one. Okay, is it right?
Yeah. Because even if systems move to the because we calculated the cost is based on watt-hours per gram, because specific energy low, so the watt-hours per gram, the cost is high.
Okay, thank you for your good answers. Okay.
Any other questions or comments? There is another question on the chatting panel. Thank you for your nice talk. Oops.
Yeah. So Professor Xia, did you read the questions from chatting room? One student asked you the role of carbon from carbon-coated LTP active material, maybe.
This one?
So one student asked you the role of carbon in carbon-coated LTP material. Yeah, maybe it's right. The role, the functions of carbon.
The function of carbon. Okay.
Yeah.
So I think this is long stories, because if we see that this next because for this one lithium titanium phosphate, if lithium, because this is a mass material at first in discharge, so this material if discharge to this in discharge to in the water electrolytes, and then how to say, because this is like because you will see if the potential is losing this line. This line is, I think, is oxygen high. This is a high water is reduced to by will reduce this one. So we must prevent the oxygen we must prevent the oxygen to reaction with the discharged lithium titanium phosphate, because this, if lithium intercalates this one, and this one will reaction, because potential discharged one, the potential will losing the water oxidation. So if there is no water, so this reaction like this, lithium intercalation compounds, there is oxygen, there is water in the electrolytes. And if we no water, no oxygen, so this reaction will, because this material will oxidize the lithium compounds. This is not reversible, cannot reversible to go back to the previous one. So we must hold the remove oxygen. So like me, we use the sealed systems. Another way is we can remove the water, but to remove the water is impossible because we in the water electrolytes. So must there is water, but we use a carbon coated layer. This is called carbon coated layer. How to say is not is porous carbon layers. So this carbon layer can how to allow the lithium ion interconnection, but it can prevent the water transport because no pore. This is the only is a crystal defect. So this only allowed the lithium interconnection. But this is a layer, so this is article. So if we have the low heat temperatures, so the electrical conductivity is low. But if high temperatures, this is becomes the graphite. Graphite is layer structured. Most is a layer structured graphite. The 001 plane is along this size. So lithium is kind of difficult to how to say divisions. So we must control the defect. Also we control its graphite this one. So this is prevent the oxygen. So reaction with the lithiated lithium titanium phosphate. So like the membrane, the porous membrane, but this porous membrane is not the porous one. This is only is crystal defected membrane. So this membrane is allow the lithium into the division, but we prevent the oxygen crossover. This one.
Any other questions? Well, I have a very general question for you.
Okay.
At the moment, 3 big countries like China, Japan, Korea are the main powerhouse as far as lithium-ion batteries are concerned. But lately, big car makers in the United States and Europe are trying to have their own battery company. And what do you think about this sort of situation, and what should be considered to keep the technological supremacy of Oriental 3 countries over Western countries?
So this is a bigger questions also. I think because maybe 5 years before, I think the electric vehicle, even in China, we think is like we think is impossible or not can commercialize the one. So we think only can use the electric vehicle, can only use the e-bus. So why there is so big markets? I think there is a large lithium-ion battery products in the Asia country, Japan, Korea, and China. But most of the markets, I think for the EV is recently is in China, because with the first time we use this is EV markets. There is 2 in China. There is 2 big markets. One is for the e-bus. For the e-bus, I think this is in China is a special market. But for the passengers car, no, over all the world. So So I think it's even included Europe and the United States, and we will be commercialized. We will be widely used electric vehicles. So for the battery systems, I think the technologies for the even for from in the view of technologies, I think even for the accurate lithium-ion batteries. So we think I think this energy only that we for the most passages they is worry as a driven resistance. This is for the worry about the specific energies. So specific energy, if we hold the compared with the fuel cars. So I think it's impossible to get the commercial traditional fuel cars. So so explore the high specific energy batteries. It's we should do, but I think this is not the one way to only the one way to for the batteries. We must think I think we must because the specific energy for the lithium iron phosphate in the channel we always we have some question So for the driving car use we call the 3 layered compounds, the cathode material and lithium iron phosphate, which technology is the best one. So maybe 2 years before we think is for the driving resistance, we should develop the 3 nickel mangan based batteries. But recently we go back move to the lithium iron phosphate materials. So I think the specific energy. So it's not the how to say for it really is for the electric vehicles. We need the high resistance, but I think it cannot compare with the fuel cars. So we think we need reduce the cost also. We the way is reduce cost. Another is also we in China we need some improve the safety. So, but for the all solid battery, I think it's for commercialize it's impossible. I think recently is impossible. Maybe we in China we call the solid state battery, not all solid state battery. We just use some solid state electrolytes to reduce the content of the liquid electrolytes. This means is one way. But even for the United States and the United States, I think for the technical technologies for the lithium-ion battery I think is good enough to serve for the electric vehicles. Problem maybe we must reduce the cost. Reduce the cost. So I think this is I think this is my opinion.
Okay, wonderful. Thank you very much, Yongyao. And if no other questions or comments in 2 seconds, I'm going to close Professor Shia's presentation, and then I'm going to. Oh, now you can close the screen share.
Okay.
From yours. So okay, so that I can. Where is it?
Picture time. Can I take a picture?
Yes, I would like to show the next seminar, and still host is not allow me to use screen share. 혜림 씨 도와주세요. Okay, wonderful. And okay, next seminar is on 2 weeks from today, April 28th, and Professor Andrea Russell of University of Southampton, United Kingdom, will deliver us on X-ray spectroscopic studies of electrocatalyst and battery material. And at the same time, I would like to remind you all, seminar report is due by noon on June 23rd. And you can select only one seminar for your report. Okay, thank you very much. And again, Professor Shah, thank you for your very interesting presentation today. I appreciate it very much.
So
Thank
thank
you.
you, Professor Kim, and all of your colleagues. So I really is very glad to share this about 1 hour for all of you. So if possible, so Dr. Lee, please also send the for the information of the next seminar. I also want to join your seminar.
Oh, you can, you are welcome to, yes, of course, you are welcome to join us.
We are the time dependent just on 1 hour, so I think it's no problem for me.
Okay.
So I also very interesting the next.
I will send you the link one day before the seminar.
Yeah.
Okay.
Thank you.
Okay,
Really,
wonderful.
thank you, all of us. All of
Okay,
you.
thank you.
Okay.
Thank you very much.
So,
Bye.
so see you.
Yes, I will see you
I
soon,
hope
hopefully.
to see you the
Yes.
very near future, maybe.
Yes, thank you. Thank you.
Thank you.
Bye.
Bye.
네, 수고 많으셨습니다.